In our trivial thread pool implementation, we are launching only limited number of threads, specifically, amount equal to the value which returned from the hardware concurrency function. In most algorithms, there may be scenarios where all these threads end up waiting for the tasks that haven't been scheduled, because there are no free threads. In such cases, with current thread pool implementation, we have no way of forcing waiting threads to execute another tasks until the result's waiting tasks arrives. In this video, we are going to add the functionality which allows waiting threads to execute different tasks while waiting. First, let me show you an example where we definitely going to need this functionality. Let's look back at our parallel quicksort implementation. Here, in each iteration, we pick a pivot element and partition the dataset in two, where lower part has elements less than the pivot value and the upper part has elements higher than the pivot value. Then, we call quicksort again for each of these parts recursively. We make recursive call with first part using current thread and recursive call to other part using a new thread. Let's say, for this example, we are going to make recursive call to the lower part of the dataset using current thread and the upper part using a new thread. So after first recursive call, we have two threads running the parallel quicksort algorithm. In the next stage, again, recursive calls would be made by selecting different pivot elements for each of these parts. So at this stage, we are going to have 4 threads executing recursive call in the quicksort algorithm. Then again, dataset are going to further partition and another set of recursive calls should be performed. Now what happens if our system is restricted to run limited number of threads only, as in our current thread pool implementation? Let's say 2 threads, for example. As you can see here, with the recursive calls with the one data chunk, it would make another recursive call, and we can consider one stage is done only after all the subsequent recursive calls end. But if we don't have enough thread to perform those recursive calls, then our application would strut as current threads are wait until subsequent recursive calls to be finished, and there's no threads to perform those recursive calls. But luckily, our previous parallel quicksort implementation, we used asynchronous tasks. So even though we spawn new async tasks in each recursive call, still operating system can run new tasks in same waiting threads. But if we use our current thread pool implementation, we are bound by 2 restrictions. First, we have only limited number of threads in the thread pool, and our thread pool cannot switch tasks, unlike task switching in the operating system threads. After it begin executing one task, it has to stay on that task until the task is finished. So, if we use our current thread pool implementation for parallel quicksort implementation, then for sure there will be deadlocks. To avoid such a dire situation, we have to provide a mechanism so that waiting thread can execute another task in the work queue. All you have to do is to provide a function in the thread pool interface so that any thread could run different tasks whenever it feels suitable. So let me add such a function to our thread pool interface. Let's name our function as runPendingTask. All it does is try popping a task from thread pool's queue and execute it. That's all. Okay, now we have a mechanism to run any task in the working queue using separate function call. Let's see how to implement parallel version of quicksort algorithm with our current thread pool. You can do this in many ways, but let me have a templated structure called sorter, and this structure is going to handle parallel quicksort. Here, we are going to have a function called doSort, which is the function we are going to make recursive calls, and, of course, we need instance of our thread pool as well. the implementation of this doSort function is pretty similar to the one we had in the previous parallel quicksort implementation. So let me quickly add those steps here. First, we have to have the return condition for recursive call, which in this case is whether there is enough elements to make another recursive call. So we can check whether the number of elements in the data chunk is less than 2 or not. If it is less than 2, we can simply return the pointer to the past dataset. Then, we have to choose the pivot element for this recursive call. In this implementation, we choose first element of the dataset as the pivot value. And, if you remember, we have put that element to the new list called results. So let me declare another list here, and then we can use splice function to get first element to the results list. And then we can set that element as the pivot element. Okay, now we have the pivot element. Now we have to divide the dataset into two partitions based on pivot value. For that, we use std partition algorithm with lambda expressions. Let me quickly add that part of the code as well. Here, this lambda expression will make sure that all the elements below this divide point are less than the pivot value, and all elements higher than the pivot value are to be in the upper part of the resultant array. Then, we can again use std splice algorithm to create new list which contains lower values than the divided value, or pivot value, from the original data chunk. And then, we can submit that lower data set with doSort function to our thread pool. So the recursive call with that data chunk will be added to the task queue in thread pool, and running thread will be execute doSort function with that data chunk. Then, we can call doSort function for the upper data chunk in this thread. Finally, we can add the results of these calls to results array and return the results list. Now, is this our final implementation? The answer is no. Here, this implementation shows what I describe in the presentation. Our thread pool has only limited number of threads, and most probably each of those threads are going to wait until the results of the lower part, which is still in the work queue, to be finished. But there will be no thread to execute those tasks. So here, to get rid of that situation, we can call runPendingTasks function in the waiting threads until the future for the lower part is ready. So here, we can simply check whether the future is ready using isReady function, and then we can call runPendingTasks function we added to our thread pool. Notice, when you check the documentation of the std future, this isReady function might not appear. It has actually suggested improvement to the future class, but it still hasn't been added to the standards. But some compilers, like Visual C++ compiler, have the option, so we can use it here. If your compiler does not have this option, then you can simply use future's waitFor function with future status in this way to check whether the future is ready or not. I'm going to attach the proposed improvement document with this video, and make sure you read that when you have the time. Okay. We are almost done with the implementation. We can then provide the function called parallel_quicksort outside to this sorter structure. This function is going to check whether the input is empty. If it is not, it's going to pass the input to the doSort function in the sorter structure. That's it. Okay. To test whether our implementation is run properly or not, I have initialized a random array in the run function, and I have passed that array to quicksort function call, and then I have printed out the resultant output. So let me run this example now. Okay, in the output, you can see that values are in ascending order, which means our parallel quicksort implementation has sorted the given array. Okay, now we have added the functionality for running pending tasks from waiting threads in our thread pool, so that we can avoid deadlocks when tasks are waiting for other tasks. But still, this implementation is far from an ideal one. When we submit a task to the thread pool, or when we call on pending tasks, in both cases we are accessing the same work queue inside the thread pool. So all these calls will be synchronized internally, and it will add a performance penalty. So let's see how to get rid of these kinds of performance penalties in the next video.